period. But remember, that Kepler's third law is that the period is equal to 2 pi a to the 3/2 divided by gamma. Gamma, again, is g times the mass of the primary. So gamma for Venus is g times the mass of Venus. Now we've got to go back to the table in the book and look at the mass of Venus. 4.87 times 10 to the 24. So it's 3.248 times 10 to the 14. So now all we have to do is solve for A. So A is equal to, the square root of gamma, not gamma, sorry, is equal to the period times the square root of gamma, all divided by 2 pi, quantity to the 3/2 power. Okay, somebody work that out for me. Okay, does anybody have an answer?
I'm still getting it.
Okay, I'll give you a minute.
Oh.
Okay, I'm back.
So I have 4.6784 times 10 to the 20.
So 4.68, let's call it, times 10 to the 20 meters. Okay, very good. That's a huge orbital radius, right? That's probably completely impractical. And the reason, well, not that you'd want to necessarily have a geostationary satellite over Venus anyway, maybe if you were living on Venus, but I don't think you can. That's a consequence of the fact that the rotational period of Venus is so large, 243 days. In fact, the rotational period and the orbital period are essentially the same. So the same point on Venus is looking at the sun most of the time. Maybe there's a little wobble in there or something. I think that's right. Okay, now it just occurred to me that maybe you would rather break up into groups and work on these. Or would you rather sort of do it all together? Somebody have a preference?
Doing it together is fine.
Yeah, I like
Okay.
together.
Now, I want to know the orbital speed. Well, we just discussed the fact that the orbital speed v for a circular orbit is the square root of gamma divided by a. And we know a, and we know gamma. So you know what? Joshua. Go ahead and tell us what V is. And let me write these down. A was equal to 4.68 times 10 to the 20 meters. And what did we say gamma was?
It was 3.248 times 10 to the 14.
Okay. So go ahead, Joshua, work out V for us. Oh, wait a moment. I made a mistake. I just realized that I made a mistake. We've got to redo this. We've got to redo A. I made a mistake calculating it. A is going to be equal to P times the square root of gamma divided by 2 pi, not to the 3/2, but to the 2/3. So I miscalculated that. So let's do that again. So what did we say the period had to be? 243 days. What was that number, Truck?
It was 2.1 times 10 to the 7 second.
Thank you. Times, now the square root of gamma divided by 2 divided by pi. Now I want to raise this not to the 3/2, but to the 2/3. Okay, so I'm sorry, I made a mistake. A is 1.537 times 10 to the 9 meters. All right, so Josh, are you there? All right, Andreas,
Yes.
go ahead and work out V for us, please.
All right. I'm getting a really small number.
Oh, you shouldn't.
I may have done a calculation error. Let me double check.
So this is times 10 to the 14 for gamma.
Yeah, I keep getting a 0.011.
Okay, it's 3.248 times 10 to the 14, right? That's a 14 there.
Right.
Divided by 1.537 times 10 to the 9.
Oh, I didn't put everything under the square root. That was
And
my
then-
mistake.
And then the square root.
Okay. I was only putting gamma under that. I didn't look at that.
Okay.
correctly. Okay, I got 460.
Meters per second.
Yes.
There you go. Okay, so it's moving very, very slowly out there at that distance. What is the orbital radius of Venus? about 1 times 10 to the 11. So this is about 1% of its orbital radius. So it's way, way out there. Okay. Now this problem is important because what are you practicing doing this problem? If you know the period P, you can calculate A, assuming you also know gamma, because you need to know what the primary is. And if you know A, assuming it's a circular orbit, you know V. Now, if it's not a circular orbit, then you have V at periapsis is the square root of 1 plus E over 1 minus E gamma over A. And the velocity at apoapsis is 1 minus E over 1 plus E gamma over A. So E is 0 for a circular orbit, so you get square root of gamma over A. Okay, so if you know the period, you know A. Furthermore, if you know the eccentricity, then you know V. Either V for a circular orbit or V at these 2 points, which are the main points of interest for us, periapsis and apoapsis. Okay. Does anybody have any questions on that kind of calculation? Good. Let's do problem 2, but I'm going to have to go back to the whiteboard.